Okay, so the second section is the following, so-called tangent vectors. Okay, now first we will study the tangent vectors in R3. Let's see the definition of a tangent vector in R3. A tangent vector let's say VP of R3 consists of its vector part V and its point part point of application, actually point of application P. So for example, a vector in R3, an example of a vector is this 1, 1, 3. So here the vector part is this 2, 2, no 2, 3, 2, and the point of application is 1, 1, 3. Okay, and how do we picture this vector? Well, we picture it this way. Okay, so this is the point P. Okay, and this is the point actually V plus P, so that this vector is just the vector V. Okay, let's say. So 1, 1, 3. So this point is like 3. So this is 1, this is 1. And the vector here is this vector 2, 3, 2. Therefore, this regarded as a point is what? 3, 4, 5. 3, 4, and 5. Okay. So this is how you picture a tangent vector in R3. Okay. So a vector in R3 is actually not a triple. It's a two set of triples. One for the vector part and one for the point part. Okay. So this VP is called the tangent vector. At any point, of course, there are infinitely many tangent vectors, right? You can choose any direction. You are, let's say, at this point, you may choose any vector, starting from this point, and each one gives you a tangent vector at the point P. All right. Okay. The set of all tangent vectors to R3 at a given point P is denoted as TP R3. So TP R3 is the set of all tangent vectors in R3 at the point P. So the point part is fixed, the vector part changes. Okay, so these are just objects like this, and V is in actually a vector in R3, but P is fixed. Okay, now the thing is that this gadget itself is a vector space. It's actually a copy of R3, right? The point P is fixed, vector part is changing, and using that vector part, you may consider this set as a vector space. So TPR3 is indeed a vector space over R. Well, I have to tell you what the operations are, right? If it's a vector space, then you have to know what the vector addition and scalar multiplication. Vector addition is defined this way. So if I take, let's say, two vectors, U and so VP and UP as vectors in R3 at the point P, then this is how we will add them up. So let me say this is, let's say V1, V2, V3, and UP is just U1, U2, U3, P. Then the sum of these two vectors is just the following. You keep the point part fixed, you just add the vector parts. So this is just V1 plus U1, V2 plus U2, and V3 plus U3 at the point P, okay? And if you have a real number, let's say A, then A times VP is just what? A times VP, A times V1, V2, V3 at the point P. This is just A times V1, A times V2, A times V3 at the point P. Okay. An important point is the following. Nope. Okay. Neyse daha fazla olmuyor. Remark is the following. We cannot add the points at different tangent spaces. Vectors of different tangent spaces cannot be add. Evet. Yani suppose we have a point, we have a vector at the point P, and we have another vector at the point Q, and P is different than Q, okay? P is different than Q. Then I cannot add these two vectors, okay? They are at different spaces, okay? This is in one vector space, which is this one. This is in some other vector space, and this is not defined, okay? So this expression is not defined. Okay. Okay. Well, first parts are kind of boring because we have to give a lot of new definitions. We have to introduce new concepts and so on. So that involves, of course, a lot of new definitions, and it's kind of boring. But this is typical whenever you start a new subject. Okay, it's like learning words. If you start, learning a new language, first you have to learn, basic words. This is what we are going. This is what we are doing. A vector field V on R3, so we will denote the vector field by V, is a function. Is a function that assigns to each point P of R3 a tangent vector VP of R3 at P. Okay. Yeah. Magnetic field or electric field or a flow of some liquid, let's say. Şöyle birazcık kaymış mı? Yok. Okay. Şimdi gerçi tekrar 4'e mi alacağım? Evet. Okay, so let's see some examples. Well, I mean, here vector field is defined as a function. So whenever you have a function, you just feed the points inside the function, and the notation we usually use is this. That's the reason. But you are right. I mean, we will actually identify this with VP. Okay. But to emphasize that, V is a function, we write it this way. Let U1, U2, and U3 be the vector fields as defined as, sorry, U1 is this one. U1 at any point is defined to be the constant vector, actually, this, okay. The vector part is always constant. U2 is this one, and U3 is this one. So these are constant vector fields, okay? At any point, U1 P is this one, U2P is this one. This is the vector in the x direction. This is the vector in the y direction, unit vector. And this is the vector in the z direction. Okay, these are constant vector fields. The collection U1, U2, U3 is called the natural frame field. On R3. A frame is this, okay? A frame is this, basically a set of orthonormal vectors at a point is called the frame. So this is a frame, and it gives us a basis of the actually tangent space at the point P. And considering these as functions, so you have this frame at all points. That's why we call it frame field, okay? A field of frames. Like if a field of vectors, instead of vectors, we have three, vectors moving simultaneously. So we have actually a field of frames, okay? And we call it frame field. This is the natural frame field because of, the way they are defined. Yes. Yeah. It is not a vector field. It's a field of frames, okay? Field of frames. You may define, field of several different objects. Field of vectors, so it's a vector field, and this is so-called field of frames. Okay. Well, we will probably maybe see later. I'm not sure, but actually, when we say a frame at a point, we mean a set of a basis, orthonormal basis of the vector space of tangent vectors. Okay, so these three vectors actually gives a basis for this, and it's an orthonormal basis. And such orthonormal basis is called usually a frame. Okay. Mm-hmm. Okay, let's move to the blackboard 5, no, 6. Yes. All right. Here's a remark. If, let's say, VP, V1P, V2P, V3P is a vector field, sorry, is a vector field on R3, then we can write VPS like this. Since it has a vector space structure, okay, any vector in this space, which space, the tangent space at the point P, this is a vector at that tangent space, can be written like this, right? This is just this real number, V1P, times the vector 1, 0, 0. Actually, I have to put this P here also, meaning that this is the vector at the point, this is a vector at the point P. And then this scalar, right, this is a real number. Of course, you know, I have to put also this P here. Sometimes we will just drop it from the notation, but you should keep in mind that this is a vector at the point P, okay? At the point P plus V3P, it's a real number, times the tangent vector 0, 0, 1 at P. And well, this is just, remember, this is just U1P, right? U1P. Bakayım doğru mu tahmin ediyorum. Yes, U1P, U2P, and U3P. Okay. So V2P times U2P plus V3P times U3P. Okay. Using our vector space structure defined, we may write this vector field as a sum of, actually, as a linear combination of 3 vector fields. Okay. Well, now the third section. Please stop me if you have any questions, okay? Evet. You mean this gadget? Yes, yes. Nasıl teğet oluyor diyorsun, değil mi? Well, same thing, you know, suppose you have straight line. What's the tangent vector? Right, it's this one, so it stays on the line also. Okay. So also in the plane, you know, you have, let's say, a plane, and you have vector fields on this plane. For example, vector field like this. All these vectors stays in the space also. Yani onda şaşacak bir şey yok. Onu söylemek istiyorum. Ambient space'iniz Rn ise, if your ambient space is Rn, then all the tangent vectors are also in Rn, okay? But if you have a object, a surface, let's say in Rn, tangent vectors to your surface may not lie on the surface, but they lie on the tangent plane to the surface. Değil mi? Sen onu kastediyorsun. Kürenin mesela teğet vektörleri kürenin üzerinde değil, değil mi? Küre çünkü eğri bir şey. Ama yani o şey değil. Ambient space'in içinde kalıyor yine. Evet. Yani burada da this plane is a subset of R3 and tangent vectors to this plane at any of its points lies in the plane. Şeydeki arkadaşların tabii onu göremediler ama. Okay. Okay, now we will give a meaning, another meaning to tangent vectors. Remember, when we say, when we are defining tangent vectors, we said it has two parts, the vector part and the point of application. So now we will see what is that application, okay? Here is the definition of partial derivative using vectors. Let f be a real valued differentiable function. So it means that this function has all its partial derivatives of all orders, okay? Differentiable function on R3, and let VP be a tangent vector. Tangent vector to R3 at the point P. Okay. Then the number, well, actually, you know what it is, but we will use a different notation. So we take our vector and we feed our function into this vector. And what is this? This is by definition nothing but the following. The derivative of f of p plus tv at the point t equals 0. So this is nothing but the the directional derivative of f along the vector v at the point p, right? Is called the directional derivative of f at the point P along the direction V. Okay. So you see why we need actually two components for a vector, tangent vector. Okay. This P is used for the point at which you take the directional derivative, and V is used for the direction of that directional derivative. Okay. And we take the derivative at the point P. So we apply this directional derivative at the point P. That's why P is called the point of application. What is the application? Application is just taking directional derivative at the point P along the direction V. Right? This is just old, directional derivative. It is nothing new. This is something you already studied in advanced calculus, but we use a different notation to denote this expression, the directional derivative. Okay, so here VP is considered as an object which eats functions, and it gives us real numbers. Okay. Okay. Okay, let me just state a fact about directional derivatives. Let's see. I guess it will not work. One of the buttons got stuck, so I have to do it manually. Oops. All right. Now this is number 2. Okay. Here is the fact. If F and VP are as above, I mean, as in the other board, then the directional derivative of F at the point P along the direction V is equal to the following. Here, VI's are the components of the vector part of the vector, tangent vector, okay? Let's see. Here, so V is this vector, V1, V2, V3. VP is the tangent vector at the point P, okay? They are different objects. All right, now let's see why this is the case. So VP evaluated at the function F is what? That is by definition the derivative with respect to T of F of P plus TV at the point t equals 0. And what is that? Well, so Vp of f is then okay. Now here, of course, V is this gadget. You apply chain rule, right? Chain rule. So this expression is just what? This is just f of P1 plus TV1, P2 plus TV2, and P3 plus TV3, right? And you are taking derivative with respect to t. How would you take derivative of this expression with respect to t? T appears in all the components or in all the variables. So I first take the derivative of f with respect to its first variable, which is x. So that is just del f del x, and then evaluate it at p. And then I take that first variable, which is p1 plus tv1, and take derivative of this with respect to t. Well, I may use here actually d notation because I am taking derivative with respect to t only. Yani aslında neyse, kitaba sadık kalayım. Fark etmez. All right. At the point 0 plus, and then I take derivative of f with respect to the second variable, and then I take the second variable. Again, t equals 0, and plus okay. All right, and what is this? Okay. So let's write one more line. Vp of p is then what? So what is this gadget? This is just derivative of this expression with respect to t. So it is just v1. From this I will get v2, and from this I will get v3. Plugging t equals 0 doesn't change anything because t disappears when you take the derivative. So the result is just what we wanted, right? So it is v1 times del f del p at p, v2 times del f del p at p, and sorry, del x del y del z at p, and v3, sorry. v3 times del f del z p. Okay. All right. Now, here is a theorem. Let me also state this. Let f and g be differentiable functions. On on R3 and VP and UP, no, sorry, VP and WP be tangent vectors. And A and B are real numbers. Be real numbers. Then we have the followings. Then first I have this. A times VP plus B times WP, right? I can do this because tangent vectors form a vector space. So I take these two tangent vectors, multiply them by some scalars and add them up. I get another tangent vector at the point P, and I can apply this to F. So I am just taking actually the directional derivative of F along this vector, okay? And what will be the answer? Well, this is just this. And the second part is I can also do the following. I can form the linear combination of the functions and take the directional derivative along a tangent vector. Again, I'll get, you know, this expression. And the third one is the interesting one. Well, actually, you already know also this one, just the Leibniz rule, right? If I take the product of the two functions and take its directional derivative, then you will get what? The derivative of the first one times the function itself evaluated at P plus F of P times F of P times the derivative of G along the vector V again. All right, these are some, you know, easy actually results. What I will do next time, I will state this theorem and then prove some of them, not all of them, probably, and remind you what we were doing. And then we will continue. So I suppose this is a good point to stop. Do you have any questions?